So we're going to be finding the area by double integration, and we're also going to interchange the limits of integration using Fubini's theorem. So the area is defined by the double integral over the region with respect to the area. So where R is the region over which we're integrating. So our example is going to be, we're going to define the area bounded by this region. So what I'm talking about is this graph, I have y is equal to 4x, which is the green curve, y is equal to x cubed, which is the blue curve, and I'm trying to find the area of this particular bounded region right here. So in order to do this, we need to determine, these limits of integration that are defined by R, and we're going to do it in two different ways. First, we're going to do a scan that runs in this orientation. So you can think about it, a printer, we're actually going to scan, horizontally. So that means the start of the scan is going to start here, and the end of the scan is going to end here. And really, I need to know, where this start of the scan is going to be, and where the end of the scan is going to be, which is right here. And we can see that it's going to be the intersection of of these two curves. I can see that they intersect at this point here, which is on that dotted line, and this point here, which is on that dotted line. So I'm going to solve the intersection by setting these two functions equal to each other. So 4x is equal to x cubed, and since it's polynomial in nature, I set it equal to 0. So x cubed minus 4x is equal to 0. And I can factor these things by factoring out an x first, x squared minus 4. And since that's a difference of squares, we get x times x plus 2 times x minus 2. So I get intersection points of x is equal to 0, negative 2, and also positive 2. The reason why there's 3 intersection points is because this y cubed is going to come back down lower, and same thing with this green graph. They're going to intersect here as well, but I'm really only asking for the intersection in this first quadrant. So we're going to use the intersection points for x values are going to be 0 and 2. And if I want to know their points, this I know is going to be the point 0, 0. You can see that by inspection, but if I plug 0 into here, you're going to get 0 back, or 0 into here, you're going to get 0 back. And this point right here is going to be the point, 2, comma, if I plug 2 into here, you get 8, you plug 2 into here, you get 8, so it's going to be 2, 8. Now I'm only asking for these vertical dotted lines, so this is going to be your start and stop, which is going to be your 0 and 2. So x is going to be bounded between 0 less than or equal to x less than or equal to 2. That's these vertical dotted lines. Now, if I want to find the bottom and the top of the scalar bar, well, they're connected to the blue function and the green function respectively. So the bottom part of that scalar bar is going to be here, and the top part of that scalar bar is going to be here. So we can see that the y values are going to be bounded between the blue and the green curve. So the blue curve being x cubed less than or equal to y less than or equal to the top is going to be the green curve, which is going to be 4x. So that means our double integral can be rewritten as the double integral from 0 to 2, because that's what the x values are defined by. The x values are defined from 0 to 2. And then the y values are going to be defined from x cubed to 4x, and that's going to be dy. And we can now we can take the antiderivative of this thing and be able to find the area of this bounded region. So first, from inside out, the integral with respect to y is going to be equal to y. So this is going to be the integral from 0 to 2 of y evaluated from x cubed to 4x dx. So plugging in top minus bottom, this is going to be the integral from 0 to 2 of 4x minus x cubed dx. Now, just like in Calc 1, I can take the antiderivative of this x function. So the integral of this is going to be 4x squared over 2, so 2x squared, minus the antiderivative of this, which is going to be x to the 4th over 4. Evaluated it from 0 to 2, so plug it in 2 times 2 squared minus 2 to the 4th over 4, minus 2 times 0 squared minus 0 to the 4th over 4. We'll see that side is going to be 0. So this is going to be 8 minus 16 over 4, which is going to be 4. So the area defined by that region is going to be 4 units. Well, 4 units squared because we're talking about an area. So I'm going to erase this, and I'm going to show you that we can switch the limits of integration. Instead of doing dy dx, what we can do is we can do dx dy. All right, so I've redrawn the region. Now what I want to do is I want to change the orientation of the scanner bar. So what I'm going to do is I'm going to scan this thing from horizontally now. Actually, this is great. Before, let's do that. Y equals 4x. So what I want to do is I want to scan this horizontally, so this way instead. Which means that the scan is now going to scan. If you think about a printer, it's going to scan from bottom to top. So that means bottom and top are going to be y values. This is scanning in the y direction. So that means now my y values are going to be defined between, we can see that it's going to be y is equal to 0 and y is going to be equal to 8. It's going to be the y coordinates of those particular points, so 0 to 8. And the x values, we have to go, the minimum value and the maximum value. So minimum x value is going to be this, maximum x value is going to be this. So now x's are going to be bounded between, well, these two particular functions. Well, this function is, y is equal to 4x, but I have these things solved for x, which means I'm going to have to solve this y equals 4x for x. So if I have y is equal to 4x, if I solve this for x, I have y over 4 is equal to x. So that means this point right here is on that linear equation, which is y over 4. And similarly, I'm going to have to solve this thing for x as well. So solving that for x, you're going to have the cube root of y is equal to x. So that's cube root of y. Now we already know that the area is going to be 4, so this is just kind of verifying that we can switch the limits of integration and get exactly the same thing back. So now what we're going to have is we're going to have the integral from 0 to 8, that's going to be our dy, and the integral of y over 4 to cube root of y, and this is going to be dx. So first we integrate with respect to x, and since this function is just 1, we're going to have the integral from 0 to 8 of x evaluated at its limits. Plugging in top minus bottom, the integral from 0 to 8 of the cube root of y minus y over 4 dy. And finding the antiderivative, this is y to the 1/3. So what we're going to get is we're going to get y to the, adding 1 is going to be y to the 4/3 times 3/4 minus, this is going to be y squared over 2, so this will be y squared over 8, evaluated from 0 to 8. So now we can plug in top minus bottom, so this will be equal to 3 times 8 to the 4/3 all over 4 minus 8 squared all over 4. And what's nice again is when we plug in 0, this will be 3 times 0 to the 4/3 all over 4 minus 0 squared all over 4. So again, that side's going to disappear. So what I'll do is I'll do the cube root of 8 first, and I'll 4th power second. So the cube root of 8, be that 3 is going to be 2, and then 2 to the 4th is going to be 16. So 3 times 16 all over 4 minus, this should be an 8. 8 squared over 8. So this is going to become 8. So this will cancel the 4. So we have 12 minus 8, which will also be equal to 4. So I'm going to show you a couple different bounded functions, and then we'll just have to determine what's the best orientation to integrate. Since we know that it's a kind of our choice, we can do it, in the y direction, or we can scan in the x direction. So I'll set it up. All right. So what I want to do is I'm going to determine the area of the bounded region bounded by these two functions. We have y is equal to x squared and y is equal to x plus 2. So when I draw these two functions, we have x squared being this quadratic equation, and this x plus 2 being this linear equation that's going to have a y-intercept of 2 and a slope of 1, so it's going to look something like this. Notice that there's an orientation that we want to scan. If we scan in this vertical direction, this is going to be easier for us to do because notice that this minimum point always lives on the blue curve, and this maximum point is always going to live on the green curve. as opposed to if we did it the other way. If I scan this way, so if I scan down here, you can see that the max and min are going to live on the blue curve here. And over here, the max and min are going to be green and blue curves. So what I'd have to do is I'd have to set this as the sum of double integrals. So, finding the intersection points, you're going to have to do the double integral from here to here. The reason why it's going to be the blue curve both times is because when you square root this, you're going to get plus or minus the square root of x. So this will be negative root x to positive root x. And then this max and min is going to be, solving for x, this is going to be x would be equal to y minus 2 to, the positive root x. But if we do it in this fashion, I don't have to split this into the sum of double integrals. I can just do a single double integral, so it'll be a little quicker. All right, so we know that this function is going to start its scan here at the intersection and end its scan here at this intersection. So I need to figure out where these intersection points lie as far as their x coordinates. So doing that, we just solve the equations by setting them equal to each other. So x squared is equal to x plus 2. It's quadratic. So set them equal to 0, so then you can factor. So I'm going to get x is equal to 2 and x is equal to negative 1. So this is going to be negative 1 and this will be equal to 2, which really tells us the bounds of where we start and stop for our scan. So our integral is going to be the integral from negative 1 to 2, so negative 1 to 2 of the integral of, remember that we have to go from the minimum function to the maximum function, that these will be functions. So the minimum function being the blue function, which is x squared. The maximum function being the linear function, which is going to be x plus 2. So this is going to be, those are dy's and the next are dx's. And now we can integrate. So integrating this, integral of 1 is going to be equal to y. So evaluating y at top and bottom, this is going to be the integral from minus 1 to 2 of x plus 2 minus x squared dx. And then integrating these, we're going to have x squared plus 2x minus x cubed over 3, evaluated from minus 1 to 2, which is going to give us 2 squared plus 2 times 2 minus 2 cubed over 3 minus, when you plug in, negative 1. And when you simplify that, you're going to get 9/2. So that is going to be our integration for that. Now B, what I want to do is I want to bound this between y is equal to 1 minus x, y is equal to 2, and y is equal to e to the x. So pause and I'll draw it. All right, so negative x plus 1 is going to be a line with a y-intercept of 1 running downhill with a slope of negative 1. Y equals 2 is going to be a horizontal line at y equals 2. And e to the x is going to be the exponential. It looks like this. So we can see that our bounded region is going to run this way. Now, similar to what we had before, we would prefer to scan this thing not in this direction, because you can see that min and max will be different. It'll be black function, green function, and min and max over here is going to be blue function, green function. So if we actually scan in this direction instead, you can see the scan from the beginning to the end is always going to be, this will be the minimum point, this will be the maximum point. So we don't have to do it as a sum of double integrals. So we can see that the y values, because we're scanning in this y direction, is going to start at 1 and end at 2. So from 1 to 2. And now your x values are going to be bounded between, these dots here. So this dot here being, well, this function, except I have to solve it for x. So x is equal to 1 minus y. And this function right here, which means I'm going to have to solve that one for x. So natural log of y is equal to x. So the line, which is going to be your minimum left to right, so your maximum, which is the natural log of y. So now when we set up that double integral, it's going to be the integral from 1 to 2, the integral from 1 minus y to the natural log of y of dx dy. And then you integrate just like you would before.